Hey everyone, Sanjay Medichurla here. Uh, Welcome to part three of my video series of computational methods. And so here we're going to do part three, which is explain and code a function that calculates a surface point, a distance r equals, shouldn't be italicized, r equals zero point 0.5 from the central helix for an arbitrary angle theta between n and the cross product t cross n, right? So real quick, let's go look at what our helix looks like. Actually, why are there errors? This should be able to run properly. Okay. Um, so our helix looks like this. Remember, just for a refresher. And so what we're gonna do is we're gonna take a circle of radius zero point 0.5, and then we're gonna kind of coat the whole helix around it. And it depends on the theta angle. So that angle, n cross t, is this binormal vector. So it's the angle between the n and the binormal, right? Um, and those are going to take on the appearance of x and y in this case. Um, so let's go back. Oh, sorry, we didn't need the stack exchange anymore. Let's go back and start. Oh goodness, coding our functions. So we're going to define a function surf. It takes in t and theta, right? And then we need to make our tangent our normal, so we can take the cross product of that and create the binormal. So tangent, sorry, equals tang of t, and then normal equals norm of t. Oh no, not capital T. So binormal equals binormal equals j and p dot cross tangent and normal. Um, and then, let's go back to this Franaisere. And so what we wanted to see was, so the tangent is, let's start from the beginning. The tangent is points into the direction the particle is moving, right, at any given point. The um, the n vector, points in the direction in which the particle is turning at any given point, and then B, the binormal, points in the direction in which uh, the particle is twisting at any point. And so I'm just curious. I want to see maybe if Wikipedia has any applications of this. Uh, so it kind of shows the diagram which we kind of discussed. I just wanted to see if it has anything related to our plight, our sort of struggle that we're going to be doing here. Um, so maybe not, but never fear, we'll still be able to solve this even without Wikipedia. Um, so let's think a little bit. So we've defined theta, right? Our theta is going to be between zero. It's going to be between our normal and then the binormal, right? Um, uh, and so um, if our theta is between the normal and the binormal, normally like the polar coordinate system, right, our thetas are just between x and y, right? So if we were thinking about this as matrix multiplication, you would say like r cosine theta or sine theta times blah 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 equals x and y. Um, but here, instead of an xy vector, we're going to use the um, normal and binormal vectors, right? And so what we're going to have to do is create a 2 by 1 matrix that contains your normal and your binormal. So the way I'm going to do that is I'm going to say j and p dot stack uh, normal binormal normal, and then I'm going to make it one axis, so it sets it as a column. And then I'm going to perform a matrix multiplication with our function. So what I'm going to do here is our surface point equals 0.5 times r times jnp dot cosine theta. Oh, sorry. And then this should be a jnp dot array. And then brackets here, comma, 0.5 times jnp dot sine theta, brackets here. And then at surface point, and then I want to return this, obviously. Maybe that wasn't so obvious because I didn't type in the return. And then so let me just print surf at 0 and 0, not 9, 0. And let's see if we can run this. Oh, nice, it ran. What was our output? Negative 0.5, 0, and 0. So what does that even mean, right? I think all of these are a little bit physically hard to understand, but so it's negative 0.5 in the x direction and 0 and 0. So it's on the bottom. It's on the bottom square right here, probably around like this plane. Um, but that's not telling us what we want, right? Because that's telling us what it is in relation to our curve, but we will actually want it, we want to know what it truly is. So what we're going to do is we need to take out how it's in relation to the curve. And so what was our curve? It was f jax, I think, f jax at t plus this. Now, if I print surf, I get 2.5, 0, and 0. Which makes a little bit more sense. It's the circle is 2.5, 0, and 0 is just a little bit down from here. And so what if I made, and that makes sense because the angle between the normal and binormal I've specified is 0. So it's going to reside on the xy plane. But our surface point is going to reside on the xy plane. So what if I change this to np dot pi? It shouldn't be a, my bad, it shouldn't be a capitalized. Parentheses. That's like what was the answer? Let's go back. The answer was 3.5, a really small value and a really small value. Um, so in such cases, uh, 3.5, I guess you can't see it on the domain. So maybe that was a poor example. But um, this is the general way of um, how we can solve our problem of creating a surface point um, that is a distance r equals zero point 0.5 from the central helix, right? All of these points, like that 2.5 point, it was 0.5 away. That 3.5 point, it was 0.5 away. Um, and so in part 4, we'll vectorize this function and generate the plot. So thank you all for joining, and I'll see you in part 4.